Okay, uh, welcome. Sorry for that little delay. So let's get started. And we're going to talk about the Kondo model today, um, the actual Kondo model with real interactions rather than the free fermion model that we discussed last time. Let's see. So yeah, so Wednesday is one of those wellness days, I think. So there won't be any class on Wednesday. We'll continue on Friday. And so let me just remind you the model that we talked about last time. You imagine that you have a conduction band, as it's called, of electrons that we call C. And this conduction band electrons can move around, say they hop from side to side with an amplitude T. So they have some dispersion. The conduction band electrons can have interactions between them, but those eventually, when we get the Kondo model, we just ignore. We assume they are accounted for by Fermi liquid type corrections, which are relatively innocuous. And then what we're going to do is imagine that there's one particular atom on site 0, which has a D level. So this we call a D level, which has some energy ED. So this is still a free electron model. So the electrons can either hop from site to site, or they can hop here and then hop back out. Okay, and so what is this ED level? Well, if this ED level was well below, suppose you had some conduction band and there's some density of states. So this is just the conduction bands. This is energy, and you plot the density of states. So if you have a band, the density of states is in some window. This is where you've got a whole bunch of states, very closely spaced, where the spacing is given by the inverse of the system size. And these are what are called extended states, where the electrons can hop around from one end of the system to the other. They're basically plane waves. Okay, but then you bring in this D level, which is only at one site. And let's say the D level is down here, somewhere at the bottom. So if it's sitting over here, this is epsilon D, then this would be a state you'll call a localized state, because at that energy, it would tunnel out a little bit. It would tunnel from here to there, and then tunnel a bit more, but there won't be any resonance, and it'll basically, the wave function will decay exponentially. So this energy level would be just, any electron here would basically be trapped on that site forever. And its wave function would decay exponentially away from that site, and so it'll be an exponentially localized state. And similarly, you would also be localized if you're above the band. That would be another localized states. So these are localized. Here, we're not even worrying about, it's simply a one electron problem. I mean, in scattering theory, you call them bound states. Okay, so the question we solved last time was what would happen if the ED was in the middle of the band. So if the ED is over here, well, it can't be localized because it's going to mix, be resonant with states that are the same energy in the continuum. And so if you started with one particle sitting on this site, if it would eventually leak out to infinity. If you just started, initial state was a particle sitting here, if the final state would be probably some kind of cat state, so the particle leaking out to the right or the left. So there'll be some S-wave-like state going out from here, which will leak out to run away to infinity. But it could take a long time to leak out. There's a certain lifetime, and you can estimate that lifetime by, and that's long. It's long because of W being small. If W is large, then it immediately leaks out. It just becomes part of the continuum. But if W is small, it can take a long time to leak out, and that's the limit we're interested in. So basically, there'll be some lifetime, and the way you describe that in Green's function is you just look at the amplitude for the electron put here at some time 0 and ask what's the amplitude. It's still there at time t. and that gave us this Green's function, whose Fourier transform, which is like a density of states, was a Lorentzian. So basically what happens is that this discrete state becomes a quasi-bound state with a certain width, and the width is this width gamma. Okay, so that's kind of what we solved last time. We took this so-called resonant level model. I should have emphasized resonant, meaning that it's part of the continuum. These two levels, this level here and this level here, are not resonant. But anything that's in the band is resonant, will decay out, has a finite lifetime. And we just computed that by just computing the DD Green's function, by just summing these graphs here. And we found that the inverse of the DD Green's, so final result after you did this, made some approximations to this integral, where just put D of E as a constant. And then what you notice is that when you do this integral, dE over I omega n minus E, so you take the real and imaginary parts, that's the same as dE times I omega n minus I omega n minus E over minus omega n squared plus E squared. And the real part, okay, it's an odd function of E. So the real part, you just assume it's 0. And that's D of E here. And the imaginary part is the integral over a Lorentzian, which you can perform. And the final answer is this. So you get I omega n minus epsilon d, which was the bare level, but now it requires a small imaginary part. And omega n is always 2 pi t, it can't be 0, so it has the upper half plane has a positive sign, negative half plane it has a negative sign. And the key question is this gamma, which is the W, because we call it the width, because if you now take the imaginary part of the density of the Green's function itself, that gives you a Lorentzian of width gamma. And if you try to interpret in terms of this experiment of adding an electron and then seeing how long time t later, what's the probability that it's still on that site? The probability will decay as e to the minus 2 gamma t, because the amplitude will decay as e to the minus gamma t, and the probability will decay as e to the minus 2 gamma t. And then you see that, so that means that GDD of t, e to the minus 2 gamma t, with some oscillatory part coming with this, we don't worry about that. And so gamma is the decay rate, and you can see it as a very simple expression, exactly what you get from Fermi's golden rule, but we've kind of derived that here. It's 2 pi times the matrix element squared times the density of states. That's exactly what Fermi's golden rule tells you. Okay, any questions on that? So that's the easy part. It's just a review of scattering theory in a different language. I forgot, did we? Yes, go ahead.
Can I ask a question? So this Lorentzian, is it related to the probability of finding a particle? Maybe, yeah, it's kind of.
Well, it's like a local density of states. I mean, the point is that all the other states are extended. So if you're very far from the impurity, and suppose let's think in terms of an experiment. Suppose I bring an STM tip and I measure the density of states. Okay, you can measure that in an STM experiment. Literally, that's DIDV is proportional to the density of states. So if you're very far from the impurity, you will just see this semicircle. Okay, but when you get close to the impurity, you will start seeing this big Lorentzian.
Oh.
You will start seeing you have to have a local probe of this. So it's the local density of states. That's what GDD is measuring. Suppose you have a STM tip, and your STM tip only couples to the D site. Then you'll see the Lorentzian only.
Oh, I see. So it's like measuring this current voltage characteristic and observing this peak in this.
Yeah, in DIDV.
Yeah.
DIDV.
Okay. Yeah, I see. Thank you.
Sure. Okay, and I've forgotten. Did I last time talk about the Friedel sum rule? I think I did, right? Yeah, I did. Obviously, I did. Okay, so you can take this Green's functions that you compute GDD and the conduction electron Green's function, and then compute from it the net change in density of electrons near the impurity. So there's of course the background density, but near the impurity there's some change. So basically, you have to just count all the electrons. So if you took this term and this term, you're counting all the electrons. But then you just subtract the Green's function that comes from without the impurity. So you get a finite answer. This is the total number you're counting, not the. I should really call it n rather than rho, because it's really changing the number of electrons, not the density. Okay, so you count the total number of electrons, and then you find, quite amazingly, just like we did in the proof of the Luttinger theorem, that this complicated expression, in this case, is exactly the derivative of GDD. So, and it's not immediately obvious, but it's kind of fun to see how that happens. When you take d by d omega of GDD, here's GDD, the original expression, this one. It has one term from here, that's the obvious one, but it has another omega there. And when you take the derivative of this omega, you'll get I omega minus epsilon k squared. But GKK also has an I omega n minus epsilon k squared right here. And those two exactly cancel. So in the end, it's just this. And then you can evaluate this just like we did for the Luttinger theorem. And you get an answer that looks something like this. It's related to the phase shift, scattering phase shift of the conduction of electrons, gives you the total change in density. Let's call this n here. Sorry. It has this expression, which I've plotted here. So when your level is way below the Fermi level, when ED is very negative, there are exactly 2 electrons on it. Now, if you took this picture where the ED was here, it's also it's obvious there's exactly 2 electrons that are on the localized level. That's the lowest energy state. But if it's here, it's not so obvious there'll be exactly 2 electrons on it, because those electrons can leak out to the continuum. But you find even though they leak out, as long as you're far below the width of the resonance, as long as it's exactly still 2, and only when you get within a window of order the width of the resonance does it change. And if this is your Fermi level, here I'm assuming, so this is some Fermi level here, which is assumed to be at ED equals 0, E equals 0. So the Fermi level is be some line over here. So these are the occupied states below the Fermi level and unoccupied above the Fermi level. And so once you get up here, there'll be 0 electrons in the state. All of these states will be. So it goes that the change in total number, not density, excuse me, goes from 2 to 0, as you see from this plot. And that's what's given by what's called the Friedel sum rule. All right, so now let's add some interactions. Let's get to the interesting part where we're going to add some interactions. So we're going to take the same Hamiltonian and just add one more term, which is UD, D dagger up, D dagger, and D, N up, N up. So it's the local interaction term on that site. And we want, of course, we're interested in the case where UD is very large. What do you think is going to happen as UD becomes very large? And there is, as we'll see, a lot of strong effects. And you can see them qualitatively just by, again, just drawing the simple pictures. Let me draw them again here. Okay, so let's take, so let me take, All right, so here's our band. We'll take a flat density of states because that's what we'll work with. This is the energy of one electron states. So these are the conduction electron states. This axis is supposed to be D of E. So the Fermi level is somewhere in the middle. And so this is, say, the Fermi level, Fermi energy, and all these states are occupied. And they're occupied both with spin up and spin down because you're ignoring the interaction of the conduction band. Okay, now you bring in with your ED level. So you put it, let's say the ED level to begin with is somewhere, let me draw it in a different color, is somewhere over here. This is our ED, it's negative, it's below the Fermi level. So this is our ED. Okay, so ED is negative, so no problem, you can put one electron in there. But now when you put the second electron, because of this term, you're going to gain some energy because you put two electrons. Each electron gains an energy epsilon d, which is negative. But you're going to pay an energy, which is plus ud. So the next level will be up here somewhere. It'll be unoccupied. And this energy is 2ed plus u. 2ed plus u. And that'll have both electrons in it. And this thing could be either up or down. Okay. And finally, there's also the empty D state. So when which you have to carefully keep track of, because when ED is negative, you gain energy by adding a particle. Oh, that's not zero, that's U, excuse me. That's U sub D. And there's an empty D state, with let's say that's somewhere here. This is the empty state, so that's energy zero. So that's our zero of energy. Okay. Yeah, okay. I mean, maybe that's the situation. All right. Okay, so this is the situation we're going to consider, where the D states like to have either up or down, but can't have both. And it doesn't also want to be empty because you gain some energy by adding an electron. So the optimal situation is we're going to take ED is equal to minus U over 2. Then, sorry, what am I? Yeah, so both the empty state and the W occupied state will have the same energy, which is 0, whereas this thing will have energy minus U over 2. All right, so this is the situation in the strong coupling limit. Okay. And it's very far from the resonant level picture that we had, where you either had both electrons or no electrons on it. Here it seems to want to be halfway. Okay, so how do we proceed in the limit of large U? Well, basically, you proceed exactly the way we proceeded. Oh, here there's some comments about the Luttinger theorem. We'll come back to that later. Yeah, so these are the three levels I've just drawn a picture of. And we're going to look at this situation and then go from there. Okay, so basically what this single level wants to do is have only either one electron on it. And now we should just think back to the Hubbard model. What did we do for the Hubbard model when we were half filling and you had a very large U? We did a canonical transformation and derived an effective Hamiltonian. And we got the super exchange term for antiferromagnetic exchange between nearest neighbor spins. Well, here we do exactly the same thing. The canonical transformation here is called the Schiefer-Wolf transformation. It's the same thing. And the effective Hamiltonian we're going to get with the super exchange term is the Kondo Hamiltonian. So this is our famous Kondo Hamiltonian, where we just say, okay, from now on, the D electron is only going, the D site is only going to have, it's going to be in this state. And we're going to get rid of these states. So we're going to eliminate these states by the Schrieffer-Wolff transformation. Okay, so how do we eliminate these states? Well, for example, you could imagine a process in which this electron, so what is the term we have left out? So what we're doing now, we take this Hamiltonian, we keep this term at 0th order. It's part of a 0th order term in the Hamiltonian. And in the resonant level model, which I should have rewritten in that equation, in this model, we keep this term and we keep this term, but this is small. So we're going to do perturbation theory in W. So W small. And what's the action of W? Well, it just converts an electron between a d electron and a conduction electron, or vice versa. So if you look at this picture, what can happen is that this electron can become a conduction electron. Now, the conduction electrons are occupied up to the Fermi level, so it can go to some state over there. And then if it can go up as a spin up, and a spin down conduction electron can come down. And this way, then you get an effective interaction, which is an exchange interaction between the spin a half and the conduction electrons. So that's basically the idea. You take this model and you do this Schrieffer-Wolff transformation, and you figure out what the effect of W is to second order in W. And what you get, just like in the Hubbard model, you got a super exchange interaction. You now get an exchange interaction between the d electron spin, which we're now going to call SD. So that's the spin acting on the d electron, and the spin of the conduction electrons on that site. Okay. So where the C0 is just the sum of CK, as I've written before. So we should go back to this picture here, the very simplest picture we had here. And it's almost like the two-site model that we have to solve for the Hubbard model. Here are two sites. But the difference from the Hubbard model is this site has the U, but this site doesn't. In the Hubbard model, both sites had a U. So that makes the answer slightly different, but not very different. It's just that the energy denominator is slightly different. So you go to second order in U, and you get an exchange interaction between this electron and that electron on that site. And that is the Kondo model. Okay, so the Kondo model is the large U limit of this other model, which is sometimes called the Anderson model, where you have, there's the Hamiltonian. You have the conduction electrons whizzing around. And if they happen to be sitting on the origin, then they can interact antiferromagnetically with the spin on the d side, which is always just sitting there. So the d electrons in this Kondo Hamiltonian never move. They're sitting right there on that site, and they just have a spin a half. They're like a qubit. So the d electrons have become a qubit, and that qubit is coupled to mobile fermions moving in the conduction band. That's the Kondo Hamiltonian. And JK, you can do this kind of Schrieffer-Wolff transformation. I believe that's done in the book, and derive this kind of expression, very similar to the 4t squared over u expression we had for the Hubbard model, which I derived. So I won't derive this. It's like 2w squared over u, and the u is replaced by a more complicated energy denominator. Actually, I'm a little bit confused as to why there are no Fermi functions here. But yeah, okay, I'll think about that. Somebody have an idea why I didn't account for the fact that the state the electron hops to has to be empty? I have a feeling you do have to, but okay. All right, I won't. I'll clarify it next time, or uh, or our meeting tomorrow morning. Okay, just something I thought of while I was working this through. Okay, any questions on apart from this issue of why there's no Fermi functions here in this derivation of JK and this Kondo Hamiltonian?
Can I ask a question?
Yes, Maria.
So we're saying that the spin SD is localized and it doesn't move, and it's coupled to this C0 operators, C0 spins, but eventually it will leak out, right? Or if you're working in the regime when it's not going to do that.
Well, so it depends, I mean, of course, what's conserved is the total spin density, but our Hilbert space has something we call the spin operator, and there's a d site, and the number of electrons on the d sites in every state in the Hilbert space is exactly 1. So if you just compute d dagger d in this Hilbert space, it's exactly 1. So formally it doesn't leak out. Now, you could say it does kind of leak out because when you derive the Kondo interaction, you have to do a canonical transformation, and your new d operator on this site is not the bare d operator of the original Hamiltonian. In that sense, it leaks out. But let's take the point of view that the Kondo Hamiltonian is a fundamental Hamiltonian. So if you think of the Kondo Hamiltonian as a fundamental Hamiltonian, then the charge on the d side is strictly 0.
I see.
Strictly 1, yeah.
I see. So in principle, if we were to take a point of view that this Hamiltonian is derived from the previous Hamiltonian, then in principle, by perturbation theory, we also need to include some other corrections, and those corrections would potentially.
Yeah.
Okay.
Would be or come on to them. However, the amazing thing is, this is what we're getting to this week or next week. Amazing thing that even for the Kondo Hamiltonian, when you get the heavy Fermi liquid state, it has a large Fermi surface. That is, you have to count these spins, even in the case where the spins are fully localized. They still act as if they are part of the quasi-particles on the Fermi surface, and the size of the Fermi surface counts the spins. So that's kind of the remarkable result, which is experimentally verified many, many times, and that's what we're going to derive. But so there are two different things. The question of what do you mean by leak out? If you mean by leak out, do they count for the volume of the Fermi surface? The answer is yes.
Yeah, that makes sense.
But if you mean by leak out, is the charge density on the d side, does it fluctuate? And the answer is no. It never fluctuates in the Kondo Hamiltonian. In the original Hamiltonian with finite W, it did fluctuate. But we accounted for that fluctuation by canonical transformation and got rid of it. And that's what happens once you get to the Kondo limit.
I see. And also another thing is that this Hamiltonian is not translationally invariant. Is that right?
That's correct. It has only one spin. So when I was talking about the Luttinger theorem, I was referring to the next chapter where we're going to put a spin on every site.
And that's going to be a lattice, right?
Yeah. So this is more formal. This is more precisely the Kondo impurity model with just one spin. The next chapter will be the Kondo lattice model, and that has a translational symmetry.
Okay, that makes sense. Thank you.
Right now, today's lecture is only about the Kondo impurity model. And in fact, for that reason, I changed the title of the chapter since last lecture. It's the Kondo impurity model.
Thank you.
So there's only one spin and there's no translational symmetry in everything we're discussing today, except my brief remark about the Luttinger theorem. Okay, so what do we do next? All right, so this was the Kondo Hamiltonian. And what did Kondo do? He just did perturbation theory in JK. So now we can assume that JK is small because JK is of order W squared. W is very small and has a U in the denominator. So JK is small. So we started with a model with a very large energy scale, which is U, or U sub D here, and you made it really huge. And by the beauty of the canonical transformation is gives you a problem where the coupling is small. So now you can do perturbation theory in JK. And that is what Kondo did. Kondo said, okay, let's assume there's an impurity, and then we have these conduction electrons that couples to it. So let's just compute the scattering amplitude for the conduction electrons to scatter off this impurity. And from that scattering amplitude, we can compute the resistivity. And what he wanted to find, and he did find, was that the resistance would start going up. Now normal metal, the resistance decreases as you lower the temperature, but it would, in the Kondo model, it decreases for a while, but once you get to a temperature, which we now call the Kondo temperature, it would start going up again to a finite value, not to infinity. It doesn't become an insulator, but it saturates, but there's a minimum. And the minimum of the resistivity happens at around the Kondo temperature. And he even gave an estimate of what the Kondo temperature is. It's not just JK. The first guess would be, oh yeah, we have an energy scale JK and the Kondo temperature should be JK. That's not right. At least for small JK, that's not correct, which is the only regime where we know how to do anything. So the calculation that Kondo did was perturbation theory in JK to compute the resistivity in powers of JK. So it turns out you have to go to, and that's why this hadn't been done before, it wasn't so easy. You had to go to order JK cubed to get the Kondo effect. You don't get it at JK squared, you get it at JK cubed. And also the perturbation theory is not that easy. The reason it's not that easy, or at least I can't just open my textbook and use Wick's theorem, because this spin operator it's a spin operator. It doesn't have the it doesn't have obey Wick's theorem. Okay, so we have to compute using other tricks. So you can do time-ordered perturbation theory, but we don't have the benefit of Wick's theorem because the spins, the spins obey the commutation relation. The spins are defined by, SI, I'll drop the D, commutator with SJ is not 1, it's I epsilon J JK SK. So once you have this right-hand term, which is not 1, you don't have a Wick's theorem. And they also spin a half, so that means that SI dot SI is 3/4. So it's S into S plus 1 with S equals 1/2. So this is the property of the spins. And we have to do a time-ordered perturbation theory to third order in GK. Okay, so this is, I'm not going to carry it out. And sorry, I'm not totally well prepared by, but it's done quite very nicely. In section 13.7, all the details are there in the textbook. Okay, now I should have downloaded a copy of that section. In fact, I have it somewhere, but I don't have it here. Let me see. Shoot. Okay, a bit unprepared for today's class. I'm sorry. Okay, so anyway, let me at least try to do a little bit of it and show you at least the general idea of how it works. Okay, so so what's your Hamiltonian? Your Hamiltonian, the 0th order Hamiltonian we're going to take H0 is sum on K epsilon K C dagger K C K. And H1, which you're going to do perturbation theory in, is going to be JK SD got into C dagger 0 sigma C 0. Okay, spin on with the 1/2 here. Okay, So you want to compute the Green's function, G of K, P, and omega. That's going to be minus the time ordered product. I mean, time ordered perturbation theory still works, but the Wick's theorem doesn't work. That's the main thing you have to. So when you actually get some multi-point correlation function, you just have to evaluate it by hand, okay? But it's not so bad as you would think. So this is CK of 0, CP dagger of tau. So you just do the usual time-ordered perturbation theory, and you'll get various terms, and each one of those terms will be time-ordered product of various. So every time you bring down a JK, you bring down 2 C's and 1 S. So you'll have some, C dagger, maybe you bring down a JK, and then you get S, and then another C dagger, sigma C, and maybe you go to next order to order JK squared, you get another SD, and they're all time labels and everything, C dagger, sigma C, dot, 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 dot. So if you go to nth order, there's all these terms. Now, one thing, now your H0, however, has some conduction electrons, which are the 0th order Hamiltonian. And what is the 0th order Hamiltonian for the spins? Here life is better. It's 0. There is the 2 states of the spin and the 0th order Hamiltonian have the same energy, they degenerate. Okay, so you can take this expression here and rewrite it and separate the product. So you can write this as time ordered product. It's inside the time ordered product, sorry. Some various C daggers, C dagger, C dagger, C dagger, so dot, dot, dot. So that's the conduction electron 0th order correlator. This is also 0. And you can multiply it by various time order product of SD. So this will be an SD of time tau 1 with some component A, SD of component B with time tau 2, SC of component tau 3. So you just factorize it. And now the question is, how do you evaluate this object? What are these time dependencies? Well, the time dependence don't do anything because the Hamiltonian is 0. So why do I even need to put the times in? I need to put the times in to figure out how to order these things. So I have to order the spins in a particular, the time ordered fashion. So is it SA, SB, SC, or is it SA, SC, SB? Which order do I write the spins? That's the only thing I need to know. That's the only dependence on the times. And once I've written them out, I can evaluate the expectation values. It's just traces over spin operators, which I can just evaluate by repeated use of the spin commutation relations. So I keep using these commutation relations over and over again, and this rule, I can work it out. So that's the only headache here. I can't use Wick's theorem to evaluate these multiple correlation functions. I have to actually do it by hand. But here I can use Wick's theorem, no problem. It's free electrons. So that's the computation in a nutshell that Kondo did. To do it at second order is not so bad. To do it at third order, it'll take a good afternoon, but it's all worked out in the book. And I'm not going to do it because eventually I will do something analogous by another method that's more powerful because it also applies to the lattice and so on. But this was the original historical calculation by Kondo. Okay, now on very general grounds, you can see that you can write the answer anyway in the following form. That it's a the Green's function of the conduction electrons. It's just the free particle propagator. And then this kind of term, where you have a particle moving freely, then a T matrix, some function of omega, times a particle moving freely. It has to be of this form. And you kind of can see this simply again by just drawing a few graphs very schematically. You have some conduction electron coming in. So now when it interacts with the spin, it has momentum k. This is jk, and there's some spin operator here. And then, it moves to some other K prime, interacts with the spin. So this is just time going this way. You get a spin operator, K double prime, and so on. And finally, it comes out, say, with momentum P. And this brings in some frequency omega. So it must come out with frequency, the same frequency, just by energy conservation, frequency conservation. So that's, that's the entire set of Feynman graphs. But now the trouble is that when I evaluate these spin expectation values, I get some complicated answer that I cannot draw in pictures so easily. But you can just see from the structure of it that whatever answer I get, it's going to be independent of K, because once this momentum K comes in, this scattering electron has a different momentum K, because the interaction, if I write it out, is the same as JK over V, sum on K and P of SD dotted into C dagger K sigma CP. So basically, we call this a point impurity, and we just have scattering that's independent of the location of the impurity. The electron can go from state K to state P, and there's no relation between K and P. They're just independent numbers, and the amplitude is the same no matter what K and P. So whatever frequency momentum I put in here, it's not going to influence the answer. And that these internal momenta are all summed over. And then I just evaluate this horrible mess, and I get some spin correlation function up there. And this whole thing is just some function of omega. So this whole object here to all orders will give me this T of omega. It's some function of omega. So the Green's function very generally is of this form. And this is exactly like the resonant level model, except when in the resonant level model, this T was just W squared. But now it's something more complicated that we have to compute. It's a function of, in particular, it's a function of both frequency and temperature. Okay, so this is the final answer up to order J cube, which is worked out in Bruce and Flensburg. This is what you get for T and omega, plus, plus all corrections to this of order JK to the fourth. Okay, Kondo didn't compute exactly this, but this is Kondo's original calculation from, I forget, 1963 or something like that. Okay, so what you find is that the leading order answer, the first term, is actually quite straightforward. So if I want to compute the scattering cross section, then you just take the imaginary part of the T matrix, and the leading term is, something pi and JK squared times the density of states divided by 16. Where is it? I think the density of states has only one density of states there. Sorry. So there's a typo there. Of course, this factor of squared is over here, not over there. Okay. And this is exactly the kind of thing you might expect from Fermi's golden rule. You have a spin which is randomly up or down. And if it's up, there's an amplitude for spin ups to scatter, spin downs to scatter, and you can flip and you just compute by Fermi's golden rule the scattering probability. You just get some number which depends on the density of states. You average over spin orientations, and you get some answer line. So this is kind of the boring answer. This is just like the spin behaving like an impurity. But then all the magic and all the interesting Kondo effect is here. You get a term that's strongly dependent on temperature. And in fact, in the limit at zero temperature, when omega goes to 0 and temperature goes to 0, it's logarithmically divergent. Okay, you compute this thing to third order, and you find a term that has a very strong dependence on temperature. So it's log of T, and it was sometimes called the Kondo log. This was first found by Kondo, and it basically, since I'm running out of time, it basically explains the resistance minimum. So what's happening here is that there's an extra correction to the scattering amplitude, which becomes larger and larger as you lower the temperature. In fact, it becomes so large as temperature goes to 0. Let's just put omega equals 0. It becomes so large as temperature goes to 0 that it's even larger than the first term. And at that point, of course, you can't trust this calculation. When this term becomes larger than this one, you stop, because then you're doing perturbation theory and your first order correction is bigger than your 0th order correction. So then you can ask what happens then when this becomes much larger than that. Okay, Kondo didn't quite answer the question. That is what's called the Kondo problem, is to figure out what happens when perturbation theory breaks down. But already in perturbation theory, you see what will happen is that this term becomes larger and larger as you lower the temperature, and that means the resistance can start to go up. So what Kondo tells you is that the resistance can start to go up, but then doesn't tell you what happens as you go to even lower temperature. So question you can ask at this point is, at what temperature does the resistance start to go up? Okay, and that's a question we can answer. Let me make another empty page. So we can say now there's a resistance minimum when this term is of order 1. So we say when jk times d of 0 times log of the band d is the bandwidth divided by temperature is of order 1, of order the first term, and we call this the Kondo temperature, dk. And so that you can solve this equation, and you find the Kondo temperature is the bandwidth times exponential of -1 over the Kondo coupling times d of 0, the density of states at the Fermi level. Okay, this would look like a very familiar expression. It's exactly the BCS type expression for the critical temperature for BCS physics. And there also, it was due to a log in perturbation theory called the BCS log we met earlier. Now this is a very different sort of log, which comes in perturbation theory of an impurity in any metal. And what it shows you is that the Kondo temperatures actually can be very small. Even if JK is 1,000 Kelvin, the Kondo temperature could be just a few Kelvin. You have to go very low temperatures because this number could be large, and so e to the minus a large number is a very small number. Okay, so as JK goes to 0, the Kondo temperature is very small, but up to the Kondo temperature and slightly below, you can just do perturbation theory. You don't need any fancy stuff. All you need to do is be able to figure out how to evaluate, these products here, which is tedious, but in principle not very complicated. The only complication now is that all these tricks I learned from diagrams, I have to be more cautious about applying. But in the end, it's just a usual time-ordered perturbation theory that you're expanding on. Okay, so that's the Kondo effect. Well, the resistance, as far as the resistance minimum is concerned, and a crude estimate, just by comparing this term with that term, at what temperature can you expect this term to start becoming important and possibly give you some upturn in the resistivity? Of course, you have to do better, and today we can do much better. We can compute the whole thing, the whole resistivity at all temperatures, using some very sophisticated computer methods. But we're still in 1960 whatever when Kondo did this very basic computation. Okay, let me make a few comments here. Right, so this term here ends up involving, again, this should kind of remind you of BCS. There also you had a 1 minus 2f of ek over 2 ek. Here you got EQ minus EK, there's some energy differences. So why are we getting energy differences here? It's a very quantum mechanical effect. And you're getting energy differences because if you look at this graph, it's like the difference between this energy, and that energy. Why are things depending on that? Well, things are depending on that because the expectation value of the spins depends upon which order you put these. So really, the Kondo effect comes from kind of interference effect between, a spin coming in and flipping this way and that way and going out, or an electron coming in and flipping the opposite way and then going out. There are two different effects that interfere, and that interference happens because the expectation of the spin operator depends on which order you flip the spins, in a very crude term. So it's a really interesting quantum interference effect, and that gives you this rather strange expression, which I haven't derived, but it's derived in the book. And maybe next time I'll be better prepared, and I'll at least flash the calculation in the book for you to see a bit more detail of where it comes from. Okay. All right. So that's just an explanation of what the Kondo Hamiltonian is and how the fact that you have an actual quantum spin makes its interaction with the conduction electron quite subtle, and gives you this logarithmic term that diverges as temperature goes to 0. Okay. But we're going to get the same effects. I'm going to eventually give you a calculation, but I'm not going to cheat at all. Which is a lot simpler and doesn't involve and works almost entirely in the framework of things that obey Wick's theorem, which is always a nicer place to be.
Can I ask a question?
Yes.
This similarity with the BCS theory, is it just a coincidence, or it somehow, like heavy fermions somehow will form this bound?
Yeah, okay, so it is more of a coincidence, I would say, but there are some similarities. So BCS you can think of as, what you're doing is you're forming a bound state of two particles. So you have to look at the propagator of two particles, and these particles can have zero energy because you're not near the Fermi level. And so there's a logarithm in the propagator of two particles. In the Kondo model, it's really a particle hole thing. There's a one particle, one hole, because every time the spin flips, it's taking an electron and converting, is taking an electron from an empty full state to an empty state. So it's a particle hole propagator. And again, these are particle hole excitations right near the Fermi level. So when you integrate over things that have some retardation right near the Fermi level, you can get logs because the density of states at the Fermi level is constant. So that's kind of what the similarity is. In this case, the log comes from the fact that the density of states at the Fermi level is finite in both cases. But one is a particle propagator, the other is a more complicated particle hole effect. Basically, the BCS log is much more robust. In fact, you can now ask, what happens if you put in other interactions, other impurities? Is the BCS log going to still survive? The answer is yes. It only requires time reversal symmetry. Whereas the Kondo log is not as robust. It can disappear. And in fact, we'll see how it disappears in more generic models. But it's certainly present. We have one impurity interacting with any generic Fermi liquid. In that case, it's present.
I see. So when you include non-perturbative effects, you will be able to exclude this log from the consideration.
Well, when you go to the lattice model, for example, this log can disappear.
I see. Mm-hmm. Makes sense.
Well, that's a topic for next week. Yeah, good. Great question, though. What was that beep? Did you hear a beep? Well, anyway. All right, so what's next? Okay, no problem. Yeah, so you can also do a computation in other quantities, like something called the magnetic spin susceptibility that I haven't talked about, but which is discussed in the notes. And the basic feature you find is the same, that that there's a temperature, the Kondo temperature, where there's a log correction, and the log correction becomes about a 1 once you reach the Kondo temperature. Okay. All right, so then, so this was understood, and then people had to understand what happens at lower temperatures. And there's a, historically a very interesting story. I mean, in some ways, you can see that the people started introducing ideas of the renormalization to this problem. And the basic idea of renormalization is that you take some correction like this. You have a 0th order term, a 2nd order term, or in this case, a 1st order term, and then you have some correction. And you think of this correction, at least from the high energy pieces, as a renormalization of the value of JK. You can think of this term as a renormalization of this JK, and you just absorb it in there. And that renormalization, that led to the invention of the renormalization group and reinterpretation of the Kondo log as a certain RG flow equation for the Kondo coupling, which I guess I'll talk about next time. The curious thing is that the RG flow equation for the Kondo coupling in this very simple problem, relatively simple, is the same as the RG flow equation for quantum chromodynamics, for the gauge coupling quantum chromodynamics. There you have something called the confinement temperature. You start with some gauge theory with free gluons, which are interacting with each other, and the coupling is this gauge coupling. But that gauge coupling becomes very strong at a certain scale, which is the confinement energy scale, below which the quarks become, protons. And that's very analogous in the end, but not exactly the same, of course, as what's happening here. Here you have a free spin, which is flipping conduction electrons willy-nilly and doing perturbation theory, but then the coupling becomes very strong. And so you can ask, what happens then? What is the analog of the proton here? Okay, I'll give you the answer next time. So the Kondo temperature is the analog of the confinement scale. The quarks are the analog of the free spin and the free electrons. What is the analog of the confining state in the Kondo problem? So that was a subject of a lot of work in the 60s and 70s, and of course we know the answer. There's even an exact solution. What is the real low temperature ultimate state of the Kondo problem? And well, you can read the answer in the notes, or I will discuss on Friday. Any other questions? Okay, then have a great rest of the day. I will have a discussion session tomorrow, and yeah, okay. See you later.